Hi, I am Dheeraj Kumar from 3rd BSc PME and my serial number is 23 according to this quiz competition. So let me start a chapter about backbone of maths is called a linear algebra, and before linear algebra first we will introduce about what is a NBAG. NBAG. N stands for number systems, B stands for binary operations, A is algebraic system, and G is called groups. So for mind map, NBAG we remember it like new bag, where EW is silent and NBAG we read it. So here is new bag. N is called number system, B is a binary operation, and A is algebraic system, G is a groups. So it's these 4 points consist and make a maths valuable points. So first NBAG we start from N is and stand for number system. So here is a number systems, or also designed here NBAG. It is number system, B is binary, A is for algebraic system, and G is for groups. So first we'll come to the number system. Number system, what is a number systems? Actually number system is all about a different types of numbers. We start in number, and we have 7 types of different number system. First is N. N is stands for natural numbers, and natural numbers counts from 1 to infinity, where like example 1 2 3 4 5 so on up to infinity. And next is W. W is stands for whole numbers, where whole number is nothing but including 0 in natural numbers is called whole numbers. Example 0 1 2 3 dot dot infinity. Then next is integer numbers. Integer numbers is a integer number starts from minus infinity to up to infinity, like examples minus infinity minus 1 so on, and minus 3 minus 2 0 1 2 up to infinity. Means we can say integer number is minus infinity to plus positives. And then next one is rational numbers. Rational numbers is a numbers that state in forms of p by q, where p and q is integer numbers and q is not a 0, then it is called as rational numbers. And next one is irrational numbers. Irrational numbers means whose numbers is we can't write in form of rational numbers or available in p by q forms is called irrational numbers. And then next one is real numbers. Real numbers is a group of or union of rational and irrational numbers. Q union q dash is called a real numbers, where we have here note q cap q dash is equal to 5, because no one number is there between rational and irrational numbers, or no one common number is there between rational and irrational numbers. So real number is a union of q and q dash. And then last one is complex numbers. Complex number is a union of real numbers and imaginary numbers, where we write it x plus iy, where x and y is a real numbers and I is a imaginary numbers, and its value is root over minus 1. So this is all about a number system. And for mind map or for briefing, we read it in one statement. This all different type of number system is Nehru went in quarantine, question raised in committee. Here Nehru means N means Nehru, W means went, I stands for in, Q is stands for quarantine, Q dash is stands for questions, R is stands for raised, and C stands for committee. So Nehru went in quarantine, question raised in committee. We study in a brief forms. And after number system we have a binary operations. So we'll come in binary operations. What is a binary operations? See, binary and operation is different. Binary means by means two. Ordinary operations is nothing but any functions works on two types of different numbers. So binary operations, here we know binary operations. Here we first define what is a binary operations. Let G be a non-empty set. An operation star is said to be a binary operation if A B belongs to G, then A star B belongs to G, where a star is operation on addition and subtractions. So after this we'll come to the binary numbers. We also designed two binary numbers in four types of operations. We have four types of operator. First is addition, second subtractions, multiplication and divisions. So first we'll see where additions is in natural number, it satisfies or not. So we'll see addition is a binary operation on natural number if and only if we'll take any two numbers from natural numbers and then we'll operate on additions. If the sum of the natural numbers is in natural numbers, then only it is in addition is satisfied on natural numbers, or addition is a binary operation on natural numbers. Like if you take two numbers, like one is 2 and other is 3, if you add 2 and 3 it becomes 5, and 5 is also belongs to natural number. So it is addition is a binary operation on natural numbers. If you see in whole numbers, again we will take any two numbers like 0 and 3. If you add 0 plus 3 is 3, where 3 is also in whole number. So addition is binary operations on every number systems, naturals, numbers, whole numbers, integer numbers, rational numbers, real numbers, and also on complex numbers. So addition is satisfy all the number systems. So addition is a binary operation for all. Now we'll see the next is subtractions. If you see subtractions is not a binary operations on n and w, means natural and whole numbers, but apart from this, integer numbers, rational numbers, real numbers, and complex number, it is on binary operations. So first we'll check on natural numbers. We'll take any examples, like natural numbers we'll take 2 and another number will take 1. 2 minus 1 is 1, where 1 is belonging to natural number. But if you take another examples like 3 and 3, 3 minus 3 is result is 0. So actually 0 is not in natural number, so it does not satisfy in natural numbers. So this subtractions, so subtraction is not a binary operation on natural and whole numbers, but apart from natural and whole numbers, integer, rational, real, and complex number, it is a binary operations. As like multiplication is also a binary operations on every ones. We'll take an examples, like we'll take a natural numbers 2 and another we'll take a natural numbers 3. 2 and 2 3 is 6, where 6 will be there in natural number. So it is multiplication is on a binary operation on natural numbers and also in all numbers. If we'll see in divisions, division is a operators. We'll see in division is also not a binary operations on completely natural numbers, whole numbers, and integers numbers for all numbers. So division is a binary operation on rational numbers excluding 0, because if you take a 0, so 0 divided by something will go outside of rational numbers. So that's including 0 is it is not a operations on rational numbers, also on the real numbers, also on a complex number. So excluding 0 in rational numbers, real numbers. So it is not on. Excluding 0, division is a binary operation on rational number, real number and complex number. So it is all about binary operations. So we'll see that rings. What is the rings? Rings in algebraic system, R plus dot is called a ring. So we define rings in algebraic systems. R with plus and dot is called a rings if it satisfies the following conditions, and condition is like ESD. E stands for abelian group, S stands for semi group, and D stands for distributive with respect plus. So we'll see by one. R with additions is abelian group, means real number is satisfied with additions is abelian group, then it is a rings. Again R with dot is semi group, is a rings. Again dot is distributive with respect to additions, is called a rings. If follows the three conditions, then it is called a rings. Now we will see the types of rings. So types of ring is, we have 7 different types of rings. First is C stands for commutative ring. U stands for unity. Z stands for zero divisors, and W stands for without zero divisors. I stands for integral domains. D means division rings, and F is field. Where we stands this series in carry, umbrella to Jew with Indian dosa and finger chips. So we'll see one by one. C is a commutative rings, and if a C is commutative rings, means commutative rings, it is a type of rings. If any rings that follows commutative law, it's called a commutative rings, and use unity of rings. So unity of rings, and Z stands for zero divisors. Like if you take any two numbers A and B, if you divide A divided by B, you will get 0, then it is called zero divisors. Like we will take examples Z6, where 2 and 3 is an elements. Two non-zero elements, after operating it gives 0 elements, then it is called zero divisors. And without zero divisors means two non-zero elements, after operating it doesn't give a 0, then it is called without zero divisors. And next one is integral domain ID, where integral domains have a part C, U and W. C stands for commutative, U stands for unity with rings, and W stands for without rings. If W stands for without 0. If integral domains is defined as like a commutative ring with unity and without 0, is called a integral domains. And next one is division rings. So division rings it defines as a unity ring with IN, it stands for invertibles. If any elements invertibles, then it is called domain rings. And F stands for field. Field is consisted two numbers. First is C stands for commutative rings, and D is division rings. So union of commutative rings and division rings is called a field. So it is all about a EST, that is types of rings. So now we will come to the linear algebra, and the part of linear algebra, first we will start from vector space. So vector space it is joined as linear algebra. First we will see how I designed that vector space and the points of vector space. First, linear algebra, actually I divided linear algebra in two types, vector space and LT. LT is called linear transformations. This is vector space. First we will see the vector space. After vector space, the next point comes V of F. It is a vector subspace, and then is there FD, that is finite dimensions. Then LI stands for linear independent, and LD stands for linear dependent, and another is LS stands for linear span, and another one more is that L dot C is called linear combinations. Last one is BD, that is called basis and dimensions. After vector space we will come to the LT is called linear transformation, and linear transformations. Next one is MLT stands for matrix of linear transformations, and next one is RNK stands for range and kernel of linear transformations. Then next one is RLT is a rank of linear transformations. Next one is RNN is stands for rank nullity theorems, and next one is NSLT, is called non-similar linear transformations. It is all about. So we'll see the vector space. Vector space, define it is a like let F with addition and multiplication is a field where the F is called a scalars and V is a non-empty set whose elements is called vectors. Having defined in with two operations, first is vector addition and second one is scalar multiplications. Vector additions means alpha and beta belongs to V, where sum of vectors like alpha plus beta is in V. And next one is scalar vector multiplications. A scalar multiplication have A, B, C, D, like this belongs to F and alpha belongs to V. So multiplication of vector and additions will be in V. V is a vector space. Vector additions is a vector fields like. So if this V is called a vector space over the field F if the following conditions or properties satisfies well, where alpha, beta, gamma belongs to V. First, V is within abelian group. If it is in abelian group under additions, then it satisfies one conditions, that is V is unable. And for abelian group, we have to understand four different types of property. And then after that, we will see apart from abelian group, we have to also see whether it is holds for any vectors or not. The first condition is A of alpha plus beta is equal to A alpha plus A beta for any scalars A belongs to F, whether it where it is a left distribution law. It is also called as scalar multiplication is distributive over vector additions. And then second one is A plus beta of, so A plus B of alpha, so A plus B of alpha is equal to A alpha plus B alpha for any scalars AB belongs to F. Multiplication by vector is distributive over scalar addition. So AB of alpha is equal to, so we'll see about abelian group. For vector space we need to see whether abelian group is satisfied or not. So for abelian group we have to satisfy it with four different properties. First is associative law, second is existence of identity in V, third is existence of additive inverse of each element of V, fourth is commutative law. If it is satisfied, then it is called as a abelian group. So the next one is after vector space we will see vector subspaces. It belongs to or it is a subset of vector space. So vector subspace will denote with V of F, and first we'll define it. Let V be a vector space over the field F and W is subset of V. Then W is called subspace of V if W itself is a vector space over F with respect to the operation of vector addition and scalar multiplication in V. So next one we will see after vector space there is a vector subspace, and vector subspace is also a subset of vector space. So first we'll define it is, we denote it W or V of F, where V be a vector space over the field F and W is subset of V, then W is called subspace of V if W itself is a vector space over F with respect to the operations of vector additions and scalar multiplication in B. See, in vector space we have 4 theorems. I will just tell about theorems, and I will not go to the so depth in theorems. So first we will see the vector space types. Vector subset, where vector subspace, let V be a vector space over the field F, and W is subset of V, then W is called as vector subspace of V. W itself is a vector space over F with respect to the operation of vector addition and scalar multiplication in V. So vector subspace have 4 difference. So I wrote that 4T means 4 theorem is there in vector subspace. First theorem is saying a non-empty subset W of a vector subspace of V is subspace of V if and only if for all alpha belongs to beta, alpha beta belongs to V, where alpha beta belongs to W, W is a vector, and alpha plus beta belongs to W, means addition of two vectors is a vector, is a first property of becoming a vector, where becoming a subspace of V, and second one is A belongs to F, it is a scalar, and alpha belongs to W is a vector, where multiplication of a scalar and a vector is a vector, second property of vector subspace. And we will see the second theorem of vector subspace. Second theorem is saying the necessary and sufficient condition for a non-empty subset W of a vector space V of F to be a vector subspace of V is AB belongs to F and alpha beta belongs to W, where A alpha plus B beta belongs to W means scalar addition of two scalar multiplication is a vector, then it is a second theorem saying. And third theorem is like, so third theorem is saying the intersection of any two subspaces of a vector space V of F is also a subspace of V, means first we will take any two subspace of a vector space, then we will do a operation intersection of both sets, then we will see the intersection of two subspaces, a vector space is also a subspace of V of F. This is the third one theorem. And fourth one theorem is saying the union of two subspace is a subspace if and only if one is contained in the others. The four theorems of vector subspace is over. Now we will come to the next. This is called linear combination. What is a linear combination? Linear combination is another operations. It combines a addition of two or many more, like multiplication of vector and additions. See, linear combination says that V of F be a vector space if alpha 1, alpha 2, alpha 3, alpha 4 dot alpha n belongs to B and A1, A2, A3, A4 dot an is a scalars. Then where A1, A2 is in a scalar, then linear combination of the vectors alpha 1, alpha 2, alpha 3 dot alpha n is, say, it is only one and only one satisfy linear combination if alpha 1, the result of alpha is equal to A1 alpha 1 plus A2 alpha 2 plus A3 alpha 3 dot an alpha n, and it is also a formula to find a linear combinations of any subspace. Linear space. The next after linear combination will come to the LS. LS is represent a linear span. Linear span says that let V of F be a vector space and S be any non-empty subset of V, then the set of all linear combination of finite set of elements of S is called the linear span and is denoted by L of S. Thus we have L of S is equal to A1 alpha 1 plus A2 alpha 2 plus A3 alpha 3 dot En alpha n, where alpha 1 alpha 2 dot alpha n is belongs to an arbitrary finite subset of S, and A1 A2 A3 is an arbitrary finite subset of F. This is linear spans definition. Now it's have one. So after it all, we will come to the linear dependence and linear independence of a vector. First we'll define this both. What is a linear dependence? Definition is like this. V of f be a vector space, finite set alpha 1, alpha 2, alpha 3, dot dot dot, or so on up to alpha n of a vectors V is said to be linearly dependent if there exists a1, a2, a3, a4 dot dot an is a scalars, such not all of them 0. Some of them may be 0, not all of them 0. This is the main factor of this, such that a1 alpha 1 plus a2 alpha 2 dot 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 an alpha n is equal to 0. Means directly we can say that linear dependence is only linear dependence if a1 alpha 1 plus a2 alpha 2 dot 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 an alpha n is equal to 0. Here some of may be 0, but not all of them, maybe all of them is 0. It is called linear dependence. And then next one is linear independence. See, linear independence is directly opposite of linear dependence. In linear independence, it says that V of f be a vector space a finite set alpha 1 alpha 2 alpha dot or alpha n of a vectors V is said to be linear independent if and only if a1 alpha 1 plus a2 alpha 2 plus a3 alpha 3 dot dot an alpha n is equal to 0. And here a1 alpha 1 equal to 0 means here all vectors will be 0, then only it is linear independent, otherwise it is linear dependence. See, difference is linear dependence. In linear dependence not all should be 0, maybe some of value will be 0, but in linear independent every vectors will be 0, then only it is a linear independent, otherwise it is a linear dependent. So we'll see the linear independence. There are three types of different theorems. Theorem first is saying a set of non-zero vectors alpha 1 alpha 2 alpha 3 dot dot alpha n of a vector space V of f is linearly dependent if and only if some one of those vectors say alpha k 2 is less than equal to k is less than equal to n is expressed as a linear combination of its preceding ones. And second theorem of linear independence is saying if a subset S is equal to x1 x2 x3 y1 y2 y3 and z1 z2 z3 of V3R is linearly dependent if and only if the determinant of all elements of a subset is equal to 0, otherwise it is not a dependence. And next one, the theorem is third is saying that if n vectors span of vector space V over a field F and R vectors of V are linearly independent, then n is greater than equal to R. It is three types of linear independent is over. Now we'll come to the B and D. Here is B and D. B and D stands for basis and dimensions. Here we have to see the basis of a vector space and dimensions of a vector space. So like first we'll see the basis definitions. A subset B of a vector space B is said to be set to the basis, that is L of B is equal to B, or B if here is also two properties. If it satisfies two properties, then it is basis, otherwise no. First condition is B is linearly independent. It should be B is linearly independent. And second one, B expands B or B generates B, then it is a basis, otherwise no. So basis is over. Now we will come to the dimension. What is the dimension? Now we will come to the FD, that is a finite and dimensions. Finite and dimensions. Dimensions is says that finite dimension. A vector space V of f is said to be finite dimensions or finitely generated if there exists a finite subset S of V such that L V equal to L of S. And finite dimensions of 5 t means 5 theorems is there. First theorem is saying that any two bases of finite dimensional vector space B have the same finite number of elements. Theorem 2 is saying in an n-dimensional vector space V of f, first any n plus 1 elements of V are linearly dependent. Second, no set of n minus 1 elements can span V. And theorem 3 is saying every linearly independent subset of finite generated vector space V of f forms a part of a basis of V. And theorem 4 is saying if V of f is finite dimensional vector space of dimension n, then any set of n linearly independent vectors in V form a basis form of V. Theorem last 5. If a set S of n vectors of a finite dimensional vector space VFF of dimension n generates VFF, then C is set to basis is V. So now we over a belonging part of vector space these things. So now we'll come to the LT, that is linear transformation, and we see the definitions of linear transformation. It is saying that let U and V be two vector space over the same field F. Over the same field F, then the mapping T where U goes to V is said to be linear transformations if it satisfies two different operations where T of alpha plus beta is equal to T alpha plus T beta, where for all alpha beta belongs to U, and second one is T A dot alpha is equal to A dot T of alpha for A belongs to F and alpha belongs to U. See, this if this satisfies two conditions, then it is a linear transformation, or otherwise. And here we can say also a linear transformations follow the distributions law, left and right distributions law. Now we'll come to the after linear transformation we'll come to the MLT, that is called matrix of linear transformations. We'll see the definitions of matrix of linear transformations is let T of U goes to V be a linear transformations from a vector space U into a vector space V. U goes to V means vector space U to vector space V. U, V be a finite dimensions m and n respectively. Also let beta 1 is equal to beta 1, alpha 2, alpha 3 dot dot alpha n, and beta 2 is equal to beta 1, beta 2, beta 3. It is an element of beta 2, and alpha 1, alpha 2 is a dot dot up to alpha n is an element of beta 1. So it is called a matrix of linear transformations. If T of alpha 1 is equal to A1I beta 1 plus A2I beta 2 dot dot ANI beta n. So after MLT, matrix of linear transformations, there is one more point that is called change of basis, but change of basis is not considering according to the exam, so we'll just leave it the change of basis, and next we'll come to the R and K, that is range and kernel of a range and kernel of a linear transformations. And definition of range and kernel is a let T, where T is a T stands for transformations. So U goes to V. Two sets are important. One is the range of denoted by R of T and the other is the kernel of T denoted by N of T. These are defined as follows. Definitions you can say let T colon U goes to V be a linear transformation. The range of T is the set R of T. T of alpha belongs to U, that is R of T is the set of all T images of the element subset of V. So after R and K will come to the R L T, that is rank of linear transformations. Rank of linear transformations. Definitions of rank of linear transformations is let T, the same definitions is coming from R and K in R and RLT, rank of linear transformations. So here we'll see that let T is to be a linear transformation, then if R of T is finite dimension, the dimension of R of T is called the rank of linear transformation and is denoted by R of T. It is all about definitions. And then after that we will come to the rank and nullity theorem, R and N theorem, rank and nullity theorem. And then after R and L we have RNSLT, that is called non-singular linear transformation. Non-singular linear transformation. Here we will see that what is saying that RNSLT non-singular linear transformations. It said that T goes U B is linear transformation. T is said to be singular if there exists a non-zero vector alpha such that 0 dash and T of U to said to be linear singular. If T of alpha is equal to 0 dash, alpha is equal to 0, where 0 is the zero vector of event term. Vector. Now we over that linear transformation, and what we studied, it is all about of map of linear algebra. And here also by this we can remember of linear algebra. Linear algebra we defined in two different parts, LT and V of S. This is LT. LT means linear transformation, VS is vector space, and LT, that is linear transformation. Linear transformations we divided in 5 different terms: NSLT, non-singular linear transformations, and RLT, rank linear transformations, R and N, range and nullity theorems, MOLT, that is called matrix of linear transformations, for remembering that or memory. RLT have one more topic that is called R and N, that is rank and nullity theorems. And vector space is a big part of linear algebra. So vector space we divided in 6 different terms. First is LC, that is called linear combinations, and LS, that is a linear span, and BD, that is known as basis and dimensions, and FT is known as finite dimensions, and LD is known as linear dependence, and LI, that is known as linear independence. It is all about a linear algebra. Now you over that linear algebra. Thank you.